right, let's get going. All right, welcome everybody. Everybody having fun, winding down the last day of this thing, learning lots of good stuff? I hope, yeah. All right, so I'm Paul Luse. This is Jim. He'll introduce himself a little bit. Squeezing compression into SPDK. How clever is that, huh? Get it? Squeezing compression into... I thought it was pretty funny. Okay, so what we're going to go over is the high-level architecture of what we've done with compression over the last, I don't know, 6 months, Jim, we've been working on this? And I'll start with a DPTK library overview, and then a slide on the crypto BDEV, which we introduced last year, just so you can see the similarities and how we sort of follow the same design pattern, both in use of virtual BDEVs and of DPTK. So it was one led right into the other very nicely. And then Jim's going to go through the details of the reduce library, which I'll save the thunder on that for him. Okay, so at a high level, you've probably seen a picture sort of like this many times. I've taken a lot of the stuff of SPDK out of this just to make it a little bit easier to see what's going on. But this could be iSCSI at the top. I've just got listed NVMe over Fabrics Target because that's newer and cooler. And then underneath that, we have the block device abstraction layer. And you can see in the BDEV layer, we've got any number of virtual BDEVs. We've got DPTK encryption. That's the virtual BDEV module. And then we've got DPTK compression, which is what we're currently work in progress, which is the virtual BDEV for compression. By the way, it does decompression too. Yeah, I know. We toyed with that feature. We weren't sure if we're going to actually include that or not, but we decided it might be useful. and then over here is what I mentioned earlier with Reduce Live, and then PMDK. So I think we might be the only feature that's using PMDK right now.
Yeah, we've got like the libpmem block.
Yeah, we've got
module, but
block.
this is really the main one.
Yeah, this is actually using it as part of a bigger feature.
Yeah,
the libpmem
kind of
block
how it was intended.
Yeah, taking persistent memory and exposing it as a BDEV. This actually needs persistent memory, and Jim will get into why that is shortly. And then, of course, NVMe down beneath. Now, because we use DPTK for a bunch of stuff, you can see we've got our environment abstraction and DPTK there as well. So that's kind of the main talking points for the compression talk, and as well as the crypto. Okay, so let's take a quick look at the DPTK libraries. There's a bunch of them up here, and I'm just going to fly through and show you the ones that we're using in this activity, right? So we've got pull mode drivers over here that we're using. We're using compressed dev.
That's crypto. That's crypto.
Crypto dev. My eyes are not that good. We're using crypto dev, and we're using compressed dev. So crypto dev and compressed dev, what those are generic APIs that the DPTK team put together with a bunch of different backing modules. So with crypto, for example, you use the same API to initialize and like Intel Quick Assist versus a software accelerated module that sits behind it. Some of the initialization is a little bit different, but submitting and completing IOs for crypto is exactly the same. And there must be, I don't know, 10 of them back there that you can choose from. Most of them are outdated, but there's a whole different series of PMDs that you can choose from, pulled mode drivers. They go on the same route with compressed dev, a single API that you can plug into and sort of decide which compression and decompression algorithm or device that you want to use. And we're going to do very much the same thing that we did with crypto, with compression. We'll start with a software device driver first, and then we will move to support QAT. So all of this right now is marked as experimental for the next release. It does work. It just started working like, 2 weeks ago. We got both compression and decompression working. But we're still lacking a lot of testing and a lot of test code, so it won't be production for another release. Okay, so let's look at the crypto in a little bit deeper detail and just sort of go through the flow so you can see how it built right into the compression. So again, over to the left, we've got our stuff on top, NVMe over Fabrics Target, iSCSI Target, whatever it is, application, our block device layer, and then you see our crypto virtual BDEV, and then a real BDEV underneath it that would be representing, you know, an NVMe device or something. So you just stack the crypto BDEV on top of it and fire away. So IOs come in from the application, they go to the crypto VBDEV module. From the crypto VBDEV module, it goes and does the encryption or decryption, depending on whether you're writing or reading. And then it heads back down to the device. Okay, so you can see here's the NVMe. Over off to the right, I've got a couple of pictures here just showing the generic crypto dev API and ASNI PMD we support right now, and QAT PMD we support right now. And the QAT PMD is backed by QAT hardware. So that's how the encryption works, and that's now fully production. So now you'll see how similar, with just a few little differences, the compression decompression came along. All right, same thing on the left-hand side. We've got the application at the top. You can see the compression VBDEV in the middle, and then an NVMe BDEV underneath it. Now you see right above the compression VBDEV is the new reduce lib and PMDK. And when Jim gets to his stuff, he'll go through all the details of what those things do. You also see we've got persistent memory shown up here in the top. And I'm going to go through the flow of what the IOs look like. And it's not 100% accurate because it would have gotten really messy because there's a lot of back and forth between reduce lib, the virtual BDEV, and the disk drive, and the persistent memory. So I'm kind of give you the high-level flow. And then Jim's got some great examples that will help make more sense of it when the slides come up. So it starts off the same way. We get IOs coming from the application. They come down to the compression VBDEV. The compression VBDEV then works through the reduce lib and the PMDK to access persistent memory for metadata operations. Right? So with compression, you never know where the data is going to be, right? Because you never know how much it compresses or decompresses. So we've got to have this metadata off to the side optimally in something extremely fast like persistent memory. So that's our metadata operations. Then the compression VBDEV fires off over to DPDK and does the compression or decompression. Okay, and then IOs come down through the BDEV just like before and over to the NVMe device. And then the same sort of picture over here, we're starting with ISA-L, which is also out of the same team that does SPDK. They have a PMD for DPDK. That's what we're functioning with right now. And then we'll add QAT support as we go along. All right, any questions on that? Like I said, the reduce lib PMDK stuff will become a lot clearer here in just a minute. I will turn it over to Jim.
Actually, I have one question.
Sure.
If you go back to previous slides, the step 3,
Yeah?
is it easy to replace everything with a new IO?
It's easy to replace
Hey, Paul,
one of
can
these
you just
libraries here,
repeat?
ISA-L or PMD.
Can you repeat
If
the
you wanted
question?
to replace DPDK for compression, you would have to, it would be a fair amount of work. If you wanted to do that with our VBDEV, you'd pretty much have to implement the same CryptoDev API that DPDK has done. But the intent is, extensibility is by adding more PMDs
Yeah.
behind that API.
I think the recommendation is if you had another engine that could do compression, you know, if you build a PMD to plug into the DPDK framework here, now not only can SPDK use it without any other modifications, but any other software out there that's using DPDK compressed dev API could use it.
Yep.
So that's kind of why they went this route with the DPDK framework to make it, you know, easier to be able to plug in new types of engines.
And this is why we did it too, right? I mean,
Yeah.
like I just said, ISA-L is out of the same team that does SPDK. We could have just tightly integrated that into SPDK and sort of controlled everything in one spot. But we're like, that doesn't make much sense for extensibility in SPDK. We'd like to be able to do other things like bolt-in hardware support or come up with another encryption, decryption, or compression or decompression module that anybody adds at some point in the future. So it's that abstract API that allows us to do that.
So basically,
If the compression is done using software, will it actually hold on to the SPDK thread, or can it be offloaded to a separate thread? Because if it's a pulled mode module, that thread will get blocked until the compression.
That's a really good question. So can I answer that question at the end of the next part of this? That's a really good point, and we don't actually cover it in the slides here today, but that is part of some of the future work. So let's cover that later. Oh, we got another question down here.
So, just logically, wouldn't the metadata right actually have?
Oh,
So just going by the chronological order here, wouldn't the metadata update to the PMEM actually happen after the compression operation, right? Or
this
It's before and after both.
oh, okay, okay.
Yeah, I would say these are kind of the 4 steps, and they go in different orders based on whether you're doing.
Yeah, like I
different
said, it'd get
operations.
really
So
complicated if I had to draw everything.
I'm going to go through
up
some
here.
very detailed examples on exactly what this looks like for
And
reads
one
and
other
writes.
question, on the PMDK, what interface to PMDK, which library in PMDK is currently being used to write to PMEM? Is it the
We're literally using libpmem. So we're
libpmem,
not
okay.
using like pmem-obj or pmem-block. We kind of have our own layout, and I'll talk about that a little bit too.
All right, thank you.
Yep, good questions. Okay. Oh,
If we use the quick assist hardware support, what's the main benefit to use DPTK?
do you want to take that one?
What was the last part of the question?
If we have a quick assist hardware support, like a GMD processor to support it, what's the advantage we also use the DPTK?
The advantage would be the software infrastructure is already plugged in for SPDK to make use of it, right? And the advantage, of course, of using the QAT for hardware offload is to free up your CPU, right, to do other things you want SPDK to be doing with it. Does that answer your question?
Just, I think I understand his question a little bit more. So the advantage in my mind is you now have one API to either use an accelerator, whether that comes from Intel or some other company, or to use software running on the CPU, or potentially to use an FPGA. So your software is just using one API, the DPDK, CryptoDev, or CompressDev API. So the advantage there is you don't have to rewrite your software to use different hardware accelerators. Yeah, exactly.
Okay.
Great, yeah, and the same applies for crypto also, exactly what Nate just said.
Okay, so I'm going to start out with an overview of what we're calling libreduce. So as Paul talked about, this is the main engine that's driving this block compression scheme. So to create one of these libreduce block devices, there's a few parts to it. So the first one is you need some sort of block device for storing the backing I/O units, basically the compressed blocks. And this is all predicated on having some sort of thin provisioning. So as you'll see later on, we're going to write compressed blocks to this block device, starting from the beginning. As we need to write more compressed blocks, we'll end up allocating clusters, but we can use the SPDK thin provisioned logical volumes here to be able to realize the compression from the operations that we're going to be doing. Next, we have a persistent memory file for all of the mapping metadata. So we're using PMDK directly in libreduce. We don't have any kind of extra abstraction for accessing persistent memory. We just decided, really PMDK is what there is today. Like there's really nothing else, and so we do those operations directly inside of SPDK. We do store a little bit of metadata on the backing block device itself. So for those that are familiar with SPDK, we have this, what we call examine process. So as block devices are found in the system, we give the other block device modules an opportunity to say, oh, I see some metadata that I understand on this block device, and it claims it, and then it can expose one or more additional block devices on top of it. So we use this in libreduce to basically put some metadata on the backing block device, basically saying it's a libreduce volume, and then we also put the path to the persistent memory file in there. So the nice thing here is that once you create this libreduce volume, when you reboot, it's just going to automatically be there again. You don't need to do any extra configuration to get that set up. And then one key part here is this is only, what we're talking about here is an algorithm for doing the compression metadata. We're using all standard compression algorithms. We're not adding a new compression algorithm for SPDK, so it's using all of the standard ones that are out there. This is just how do we do the mapping in metadata in the persistent memory to store all the compression mappings. Okay, so I'm going to go into a little bit more detail on how this is integrated. Paul touched on this earlier, but one of the key points here is that this libreduce library is completely independent of the SPDK BDEV layer, right? So we've designed this so that it can be, you could theoretically pull it into other storage frameworks. It works really nice for when you're doing unit testing. So this is kind of showing, this is indirectly going to be showing some of the operations that Paul was talking about earlier, how the SPDK BDEV module that's built around this library, how it interacts with the library. So at start, we've got the SPDK reduce vol init. So this is basically where you are saying, I want to create a reduce volume, and you specify actually a path to the persistent memory file system. So basically, then PMDK is going to create a file in that directory based on the size of metadata that it needs for the size of the volume you specified. And then the SPDK reduce vol load, at any point later, once we have a block device, we can basically tell SPDK reduce to try to load a compressed volume based on what's on that device. If it doesn't find the metadata, it's going to return an error. And that's perfect, because that's exactly what we want. As we go through this examine process and start looking at all the BDEVs that are getting exposed in the system, this is what allows the BDEV module to be able to determine whether it should claim it or not. Once that's set up, then we can do normal read V, write V operations to the top end of the libreduce. And then based on those operations, we'll get several different operations that are coming out of the libreduce volume. So one of them is pmem persist. So if you've been at any of the PMDK talks, you know that once everything's mapped, you just do load stores to it directly. There's no extra API you need to do there. But the pmem persist is really important because when we start talking about the metadata, we have to make sure that data is persisted in a very specific order. And so we'll make calls out to pmem persist to make sure that that happens. Then we'll get read V, write V, unmap operations to the backing device for any of the compressed blocks. And then we'll also be calling out to be able to do the compress and decompress operations to whatever accelerators or optimized software routines that we have available on the system. So a few key points. I touched on this already. This is completely independent from the SPDK framework and the BDEV layer. So again, it makes it really nice for doing unit testing. It also kind of clearly does a demarcation between where the BDEV layer stops and where the compression algorithm starts. One decision we made in here, I'm going to talk a little bit about this chunk size, but the library is based around the caller knowing what the chunk size is. So what's the granularity that we're going to be compressing data on, 16K, 32K, 64K. And when it is sending I/O to this library, it expects that those I/O do not cross those boundaries. We could have, and we talked about putting splitting code inside of libreduce. Splitting code is awful. It's really nasty. We already have it on our SPDK BDEV layer. We actually have some on our SPDK NVMe driver, and we decided, let's just leverage what's already there in the SPDK BDEV layer to do that splitting rather than adding it to libreduce. So it's a restriction we have in the library, but there's other code in place that already does it, so it's actually a fairly easy one to adopt. And then it's single-threaded. So for each compression volume, it means all the I/O should be coming in on one thread only. So we're not doing any kind of locking inside of libreduce. We expect that any I/Os for that volume are all coming in on one thread. This is actually a fairly common paradigm we have in SPDK. There's a few other places where we have similar things. It's fairly easy to do message passing. And the other thing is that for most of the SPDK use cases, for example, like exposing one of these volumes maybe to an NVMe over Fabrics initiator or to a VM via vhost or an iSCSI initiator, that volume is only going to be accessed on one thread anyways. So Yes, if you were accessing it from multiple threads, there might be a little bit of a latency or performance impact, but in the vast majority of use cases, this is exactly how it's going to be used anyways. Okay, so talk a little bit about the layouts. So the yellow is basically going to represent the SSD. This is what we're calling the backing device, and we split this into I/O units. The typical I/O unit is going to be 4 kilobytes. So even if the backing device is formatted as a 512-byte LBA, the default is we're going to be writing to the backing device in 4K chunks. And this matches how most of the NVMe SSDs today are implemented anyways, where if you try to do sub 4K, it's going to do read, modify, write. So we really want to read and write in 4K chunks. And then we have the persistent memory file. And so all the metadata that we have for this algorithm is based on what we call chunks. And so a chunk represents, the volume has a chunk size. By default, we're doing 16K. It could be bigger. This is what we're picking for default now. As we get into performance analysis, we may decide to change that. But basically, this chunk map, each of these entries here in the chunk map are going to represent a 16K block of what we're going to call logical data. And you're going to see this pop up here in a second. So this chunk map contains a bunch of chunk entries. We have enough here to cover the entire volume, plus a few extras because we never want to update these things in place, right? We're very concerned about atomicity here, and so this is writes to this compressed volume are completely, they're atomic. So we won't get any torn writes, and so we allocate a little bit of extra space here in the chunk map to make sure that we can do that. So this here kind of shows how one of these chunk entries maps, maps to the blocking devices. So for example, let's say you had 16K of data and you ran it through the compression engine and it compressed down to 10,121 bytes. So we know, you round that up, that means we're going to need 3 4K units to be able to store that data on disk. And so this is where we're saying, okay, the data for this chunk is in I/O units 1, 2, and 5, and then we save the total amount of valid data that are in those I/O units. And then last, we have a much smaller portion of the persistent memory file for the logical map. And so this is basically where when a user comes in and they say they want to read something from offset 48K into that logical volume, it says, okay, well, the information for that chunk is in chunk map 2. We go here and look at the chunk map. Then here we can go get the data, and we can read it and send it back to the user. I'm going to go into a lot more detail on this step by step on how this works.
Why are you storing the size there? I mean, surely all you need to care about is that you're storing it in 3 I/O units, and so you've got a size there, and you know it's a chunk, so you know what the other
Yeah, so when you do the decompress, there's some frameworks where they want to make sure that they know exactly how many bytes, so that if you told the compression engine, hey, here's 12K of data, but really only 10K of it is valid, some frameworks may not be able to handle that. It would be nice if we didn't have to store it. I hear what you're saying. Okay, so let's go into a very specific example here. So let's say a user wants to write 4K at offset 0 into this logical volume. So the first thing we're going to do is we're going to look up in the logical map entry 0K, and we see that there's nothing there, right? So it's empty. So we don't need to go, there's nothing we need to go read. We're starting with an empty slate for this chunk. Next thing we do is we go and we allocate an entry in the chunk map. So we're keeping a list of what the free chunk map entries are here, and we pick the first one off the list. So we say, okay, we're going to use chunk map entry 0. Now we're going to compress that chunk data. And I think this is getting back to sort of the order of operations, right? We're not actually writing the metadata yet. First thing we're going to do is we're going to go compress this data. The user's only written 4K of data, right? So the rest of the 12K is going to be zeros. So we can compress all of that. Let's say this compresses all the way down to 2,500 bytes. 2,500 bytes we can fit in one of these 4K I/O units. So we just need to allocate one backing I/O unit. And again, we keep a list of which of these backing I/O units are free. We keep that in software, and we're going to allocate that first unit. So now we can go write the compressed data to the SSD. We write and persist the chunk entry. So this is really important, right? Because the next step here is writing and persisting the logical map entry. What we don't want is a case where the chunk map has been partially written and then this gets written, right? Once this is written, it means that it's valid. So we have to make sure that all of this data has been written and persisted before we write this. Does that make sense? Okay. Okay, so now let's go to so this is another fairly simple case. So now we're writing 16K at an offset. This is, this is actually, that's why we've got this example in here. So we're writing the full 16K. In this case, though, we go and try to compress it. It compresses to 14,000 bytes. So it doesn't make sense for us to write the 14,000 bytes, right? Because 14,000 bytes is going to take 4 I/O units. So instead, we're just going to write the uncompressed data to the backing volume, right? Because now we save, later when we have to go read that data back, we won't have to do a decompress operation and we'll save time. So yeah, here we're writing it because this 14,000 bytes would require 4 of these I/O units anyways. So same thing here. We go and we write the data to the chunk map. Since we've written this tells us later on, we know that this is our clue that when we read it back later that we won't have to decompress it. And then same thing, we write and persist the logical map entry. Okay, so next, now we're going to go write data to a chunk that's already been allocated. So now we look up in the logical map, we see that entry 0, there's something already there. So now we've got to go start a decompress operation. So now we go and we look at this chunk map, we say, we've got to go read this backing I/O unit. We know that that's going to compress into 16K, right? Because everything, when we compress it, it was 16K, so we should always expect when it comes back that it's going to be 16K. At this point, then we merge in the 4K of data that's coming in, and now we do the same process for when we're doing the normal write operations. The key part here is that we allocate a new chunk map, right? We don't modify this one at all, so we allocate a new one. Let's say we compress this data down to 5,000 bytes. That means that we need 2 of the backing I/O units. You round this up to 8K, so we need two I/O units. We write the compressed data to the SSD. Now we write and persist the chunk entry. So now the data this is persistent here. And now we can overwrite that entry in the logical map. So the nice thing here is if the system crashed between this point and this point, we're either going to get all of the old data or all of the new data, right? So this is kind of what makes sure that we get these atomic operations. Any questions on this so far? Except for Felipe?
I actually have a list of questions, but I would just take the most important ones. So your atomicity guarantees that on crash you can probably do a full scan on your chunk map or whatever and find what's not being referenced by anything and then recover.
That's yeah. So
that's right,
right? There's really no crash recovery. We use the same method to rebuild these lists on either a normal shutdown or a.
Well, if you wrote to the backing I/O units and you wrote to the chunk map, most importantly, and then you crash.
Yeah.
Before you wrote the logical map. When you recover, you need to free that chunk map, for example, because you don't know how much of it you completed.
So whenever we reload, actually, I think I've got a slide on the recovery process. So let me.
Okay. So
I can go through it. I can go through it now.
On this area was to do with parallel access. So if a client writes to the same virtual address from multiple queues in parallel, technically it is the client's problem that he doesn't know which write is going to complete first, which data will persist. But in this case, what happens if you write to 2 OBs at the same time? Could you end up overriding each other on the chunk map?
So we keep track of the outstanding writes, and so if you've got one that comes in and it gets in the middle of this process, then we hold the other one until this operation's complete.
Take a wrench lock or something like that?
No, so it's all on, so this is all single-threaded, right? So yeah, maybe
Okay.
you stepped in after I mentioned that, but it's, yeah, this whole thing is single-threaded, so we expect that all operations coming in for one volume are on the same thread.
Okay.
Yeah. Hold on.
So my question is, how about the partial write of the existing data? For example, previously, suppose we have the offset equals to 0, and we write 64 kilobytes. Then we write the offset beginning at 32 kilobytes to 64. So it means that, according to my understanding, you need to create 2 new entries and replace that, right? Since for the beginning, from the 0 to 32 kilobytes, the data is not, replaced. But in the first write, you will only have one entry, contains all the compressed data.
So you're asking about the case where the user does a write that's bigger than this 16K?
No,
and it has to
no,
get
I
split?
mean that just the first time you write from 0 to 64 kilobytes, and the second is the offset is 34 kilobytes, and the length is 32. I mean that just the partial write the half. So well, this algorithm create two entries, 2 new entries, right?
It would just be, so it would only ever be one entry, because we know that any incoming writes cannot span one of these chunk boundaries, right? So as long as, if you do a write and it's only to partial, let's say it's 34K to 40K,
Okay.
then it'll just be one new chunk entry, and we'll invalidate the old one.
Okay.
Okay. We can sync up, let's sync up afterwards if there's still more questions on that. Okay, so then at this point, after we've written these, we can go release these old chunk entry and IO units. But when I say release, it's just in software, right? We just update our internal maps on which ones can be used. Okay, trim. So trim is actually really easy, right? At least in this case where you're trimming a full chunk. You basically, yeah, so here we're trimming a 64K. We look up the chunk map entry. All we have to do is literally clear and persist that logical map. There's nothing else that we have to do, because now once we've cleared that, it is implicitly invalidated this chunk map entry because nothing's pointing to it anymore. So we can release all that. One thing that I missed in here is actually it's also going to go ahead and trim those backing IO units as well.
So what if you want to trim the back unit 0 that now is released?
Oh, you mean,
For secure erase or something like that?
do you mean here in the chunk?
I mean the chunk 0 you just released.
Oh, yeah.
Trim that slot 0 in the back unit.
Yeah, really, any of these cases, when we release a backing IO unit, we're going to be doing a trim here. I don't think I listed it here in the steps.
You mentioned it's just a logical map, so we'll actually do the trim.
Yeah. My point was that we don't have to make it invalid. To basically release it, all we have to do is clear it here. We're still going to trim the backing IO unit. We wouldn't technically have to do it, but we will just for performance reasons. Okay. Is there a question? Are we on time here? Okay, doing a read. Yeah, so this is fairly straightforward. We're going to go ahead and read these backing IO units. Once we've read that data, then we can return the portion that the user has requested and send that back. So let me actually cover your recovery mechanism. So when we come back up, we can easily rebuild the chunk map entries and the backing I/O units by simply walking this logical map, right? So even if there's stuff that's in this chunk map, if nothing here is referring to it, then that chunk map entry, it's not being used. So we can easily, from here build out what are the chunk map entries that are valid, and then from there we can also follow and see which of the backing I/O units are free. So it's a fairly simple, fairly quick process to be able to work through that. Okay, next steps. So Paul already mentioned the master branch has the full init load read-write path all working with PMDK. We actually do not have persistent memory units in our lab, but PMDK will work with devices that are owned by the kernel, right? It's just when you do that pmem persist, it's an msync, which means it's a disk I/O, write, which is much more expensive. But the nice thing, it means you can completely test all of this without even needing persistent memory DIMMs. We still have to do some work on the unmap part, especially unmapping sub-chunk allocations. There's still some work that needs to be done there. There's some I/O path optimizations. There's some cases right now for just simplicity to get this up and working. We're doing some copies, and those can be removed. And then we want to store some additional on-disk metadata parameters. So right now we're kind of making some assumptions on what the algorithm that we're using, and that's fairly straightforward, but it's just not something that we've gotten implemented yet. And I think that's it.
I actually had a question, Jim.
Uh-oh.
And then we'll go to you, sorry. So let's say you had a situation where you want to maybe have some compression on small blocks, but you also knew that for your workload you were going to have a very large block compression required. Could you have multiple instances of this virtual BDEV running at the same time,
Yep,
doing
absolutely.
different?
And I think that's actually how it's going to work most often, is you may have 128 of these compressed volumes that are spanned across a bunch of different cores, and they could each even have different parameters. But yeah, absolutely, this can be stamped on multiple times on any of the cores.
Thank you.
And do you have any performance results? I'm wondering what the impact is of compression on bandwidth and latency.
We don't have any performance results yet. The biggest thing is we need to get systems that our team needs to get systems with persistent memory to be able to run those. Because right now, every time we do one of these persist operations, it's an I/O write to disk through the kernel. So that's not going to be the most efficient right now. So that's definitely on our short-term roadmap, though, to get some good performance data. Oh, hold on.
How do you guarantee that your logical map is always consistent? It seems that you kind of assume that, right?
When you say consistent.
Yeah, so in case of power failure, is there a possibility that the data you are writing is always atomic? Is there a possibility that it's broken?
Yeah, so I think the way that we've set the algorithm up, let me just kind of back up here, is that we specifically, let's go back. So here we're very careful to, for example, here we start writing data to these backing I/O units, but we don't update any of this data until all the data's been written to the disk. If the system crashes while that data is getting written to the disk, that's fine. We still have the old metadata in place. Even after the data is written to disk and then we go and update the chunk map, even at this point, if it crashes, it's okay, because we still haven't updated this here, right? It's still pointing to the old entry. And so then finally, here, once you change it, this is atomic, so it's an 8-byte. It's an 8-byte atomic, exactly. So that's the only, yeah, so I mean, this only works if you can do 8-byte atomic writes on your CPU architecture. Yep, good question. We got a question here, Chinyong. Oh, you got the mic already.
So my question is, so I'm wondering the reason we use persistent memory to store metadata is in consideration of the performance, or can we just, it's just, so can we store the metadata in like a normal SSD if we don't have PMDK available?
So yeah, you can. In fact, PMDK does support that mode of operation.
Yeah.
But the problem is that it's much more expensive. Like here, when we're doing we're just updating 8 bytes.
Yeah.
That's a full block write to the backing device.
So here we use persistent memory to store the metadata is more about considering the performance, right?
Absolutely. Yep.
Okay.
Yep.
Okay. Thank you.
And then there was a question. What was the? Let's go back to your question.
Yeah, my question was that when you're...
Oh, yes. I remember now. Yeah, go ahead and ask it again.
Because when you're compressing, the compression is going to hold the thread down, and SPDK is a hold mode rate. So how does that work?
That's a fantastic question. So I don't know if you had a chance to attend the talk that Ben Walker and Darek did. So a lot of the scheduling stuff that Ben's been talking about, we're hoping to be able to utilize here. So for cases where you're doing it in software, what we'd like to be able to do is start 1, 2, 4 of these SPDK threads, and you kick the compression operation over to that so that it doesn't impact the other threads. We think if you're offloading it to hardware, you'd probably just do it in line. But yeah, that's a really good point. That's something we definitely want to do because otherwise, because compression's expensive to do in software. So yeah, we want to get that offloaded so it doesn't impact other operations happening on that thread. We're not there yet, but that's in the plans.
And then how is that going to work when you may have multiple writes coming in for the same LBA from different threads?
Well, so the libreduce is going to keep any overlapping writes to the same chunk queued. So
libreduce is not parallel in that sense?
Yeah, libreduce, it's only single-threaded.
Okay.
So it will issue multiple, it will issue operations on multiple chunks in parallel, but not operations on the same chunk.
Okay.
Yeah.
A separate one I had is on your first slide, you put only NVMe as a driver available for this. Could that work on top of, for example, Verdeo SCSI? And if so, are the sizes 16K, 4K, etc. for backing IO units or for the logical map are disconfigurable?
It's all configurable, yeah.
And it would work on Verdeo SCSI?
Yep.
Okay.
I'm getting my exercise in today.
So Jim, are there any calculations on the amount of metadata for a given size of the encrypted volume? Like what percentage of the metadata?
What percentage of what percentage of the metadata? Yeah, so right now these IO units we use 8 bytes just to kind of get around the 32-bit problem. So we've got about 32, I think we're doing 40 bytes. We don't use the full 40 bytes. We don't need the whole extra 8 bytes to store this number. So it's like 40 bytes per chunk. So you kind of work the math out, it's about maybe 0.25%. So if you have like a 1 terabyte backing device, you're going to be at about 25 gigabytes of persistent memory. Is that right? No, 2.5 gigabytes. Just a factor of 10. It's not much. Yeah, good question. Oh, another one from Chunyang.
So another question is, does libreduce provide any check procedure for data integrity, that kind of thing, or just to make sure that the data decompressed is the right data?
Yeah, I don't. Do you want to talk a little bit about the decompression operations?
Yeah, I'm not sure that we've got anything built in there for that. I'd have to go look at the compression, decompression algorithms that we're using.
Yeah. So decompression or compression algorithm, they have their own check procedure to make sure the data. But so I'm wondering if the libreduce have another check, or we just use algorithm.
It totally relies on whatever, libreduce relies on whatever Paul returns to me. So if Paul says,
I check it
Paul
myself
said,
personally.
so if the Quick Assist engine says like this is supposed to decompress into 16K and it didn't, or it was corrupted, Paul's going to return to me and say like, dude, I couldn't decompress this data, and so then that's going to be a failure, an I/O failure back up the stack.
Yeah, we've still got a lot of negative testing to do and a lot of test code to write, so we still have a lot of learning to do to get this fully functional.
But I think the answer is that that's going to be in compressed dev as opposed to
Right, yeah,
Libreduce.
it's part of the back end. We're just sort of traffic cops and metadata layout people.
Yeah.
Any other questions? Okay, don't forget, in about 5 minutes, we're going to do the drawing for all the prizes. But thanks a lot, Jim,
Yep.
Paul.
Yeah, thanks everybody. Good questions.